Welcome to this lecture on canonical forms of first-order partial differential equations. Imagine trying to read a book while riding a bumpy roller coaster. The words are bouncing everywhere, making it impossible to focus. But if you step off the ride and sit on a quiet park bench, the book is perfectly still and easy to read. The book itself did not change, but your perspective did. In mathematics, finding a canonical form is exactly like moving to that quiet bench. It is the simplest, most standard way to write an equation by changing our perspective. Now that we understand the goal is to change our perspective, let us look at why this concept matters. When we have a messy first-order partial differential equation, the variables are tangled up and incredibly hard to solve directly. By finding the right new variables, we untangle the equation, turning a complex problem into something that looks like a simple solvable equation. We transform the equation into a simpler coordinate system using new variables, typically called xi and eta. In this new system, the equation is stripped down to its most basic structure, usually eliminating one of the partial derivatives entirely. This means the equation will only have a derivative with respect to xi or eta, but never both at the same time. Before we solve anything, let us look at the formula that makes this transformation possible. This formula comes from the need to find specific paths called characteristics along which our complex equation simplifies. For a general partial differential equation, we identify the coefficients a and b, which multiply our partial derivatives. The characteristic equation is simply the derivative of y with respect to x set equal to the ratio of b over a. The coefficient a represents how the function changes in the x direction, and b represents the y direction. By solving this ordinary differential equation, we find a family of curves. If the coefficients increase or decrease, the slope of these characteristic curves changes, altering the path along which information travels in our physical system. Now that we have our formula, let us see this with a concrete example. We are given a simple partial differential equation with constant coefficients. The derivative of u with respect to x plus 2 times the derivative of u with respect to y equals 0. We are asked to find its canonical form and general solution. First, we identify our coefficients. The number multiplying the x derivative is 1, so a equals 1. The number multiplying the y derivative is 2, so b equals 2. We chose this characteristic equation approach because it will give us the exact paths where the equation simplifies. We plug a and b into our formula, giving us a slope of 2. Integrating both sides with respect to x gives us the equation of our characteristic curves. Y equals 2x plus a constant c. Continuing with our solution, we need to define our new coordinate system. We rearrange our integrated equation to isolate the constant c, giving us y minus 2x equals c. We define our first new variable, psi, to be exactly this expression. This guarantees that along these specific lines, psi remains perfectly constant. For our second variable, eta, we can choose absolutely anything simple that is independent of psi. The easiest choice is simply to let eta equal y. Next, we must calculate the partial derivatives of both new variables with respect to the old variables, x and y. The derivative of psi with respect to x is negative 2 and with respect to y is 1. For eta, the derivatives are 0 and 1. We do this because we need these 4 pieces to apply the chain rule in our next step. Let us finalize this example by substituting our values back in. We place our original coefficients and our newly calculated partial derivatives into the grouped chain rule equation. We multiply the numbers and add them together for each group. Notice what happens to the coefficient for the xi derivative. 1 times negative 2 plus 2 times 1 is exactly 0. This completely destroys the first term just as we mathematically planned. We are left with 2 times the eta derivative equals 0, which simplifies to our beautiful canonical form. The derivative of u with respect to eta is 0. This means the function only depends on xi. Replacing xi with our algebraic expression gives the final answer. Physically, this means the solution is a wave or profile that remains constant along the lines where y minus 2x is constant. Before we look at a more complex example, let us see this transformation with a concrete visual. On the left side of the diagram, you are looking at the original x and y coordinate system. Notice how the characteristic curves are messy, tangled, and intersecting. This represents how complicated the original partial differential equation is to solve. The bold arrow represents a mathematical transformation into the new xi and eta coordinate system, shown on the right. Look at the horizontal axis labeled xi and the vertical axis labeled eta. In this new space, those exact same messy curves have become perfectly straight, parallel horizontal lines. This geometric straightening is exactly what the canonical form achieves. It teaches us that by simply changing our perspective, a tangled mathematical web becomes beautifully organized and easy to solve. Now that we have seen a basic example and its visual representation, let us look at a slightly harder example where the coefficients are variables, not constants. We are given the equation x times the x derivative plus y times the y derivative equals to 0. We are asked to find its general solution. We start by identifying our key coefficients directly from the equation. Here, a is the variable x and b is the variable y. Because these are not constants, our characteristic curves will not be straight lines. We substitute these into our characteristic formula, giving us the derivative of y with respect to x equals to y over x. To solve this, we use the method of separation of variables. We algebraically move all y terms to the left side and all x terms to the right side, preparing us to integrate. Continuing with our variable coefficient example, we now integrate both sides of our separated equation. From basic calculus, the integral of 1 over a variable is the natural logarithm of that variable. This gives us the natural log of y equals the natural log of x plus a constant of integration c. Having logarithms everywhere makes the algebra messy. To fix this, we cleverly rewrite the constant c as the natural log of a new constant k. Using logarithm rules, we combine the terms and drop the logs entirely, leaving us with the simple equation y equals k times x. Finally, we rearrange this to isolate the constant k on one side, giving us y divided by x equals k. This ratio will become the foundation for our new coordinate system. Now we define our new variables. We set xi exactly equal to the ratio y over x, ensuring it remains constant along our characteristic curves. For eta, we choose the simplest independent option and set it equal to x. Next, we calculate the partial derivatives. The derivative of xi with respect to x requires the quotient rule, giving negative y over x squared. The other derivatives are straightforward. We substitute these expressions along with our original variable coefficients x and y into the grouped chain rule formula. This step looks algebraically heavy, but it is just a direct substitution. We carefully place each algebraic fraction into its designated spot. We do this to see if our choice of xi successfully eliminates the first derivative. This brings us to the final answer for our second example. We simplified the large algebraic expressions inside the parentheses. Looking closely at the coefficient for the xi derivative, the terms multiply out to negative y over x plus y over x. These perfectly cancel each other out to 0. The first term completely vanishes, leaving us with x multiplied by the eta derivative equals 0. Assuming x is not 0, we divide both sides by x, arriving at our clean canonical form. The derivative of u with respect to eta is 0. This means the function relies solely on xi. Substituting our original algebraic expression for xi back in gives the final general solution. Physically, this means any mathematical function whose input is the exact ratio of y to x will perfectly satisfy the original equation. So, we have successfully used this formula for both constant and variable coefficients. This brings us to the proof of why this transformation works. We are setting out to prove how the general partial differential equation transforms into its canonical form. We start with the most general way to write a first-order linear equation, with coefficients a, b, c, and d. To change our perspective, we introduce our new coordinate axes, xi and eta. But we cannot just swap the letters. We must use the chain rule from calculus to carefully rewrite our old derivatives in terms of our new variables. The change in u with respect to x is split into two parts: how u changes along the xi direction and how it changes along the eta direction. We do the exact same thing to find the derivative with respect to y. This sets the foundation for our substitution. Continuing with our derivation, the next logical step is to take these new chain rule expressions and plug them back into our original general equation. This direct substitution replaces all the old x and y derivatives with our new xi and eta derivatives. At first glance, this new equation looks much messier and more complicated than what we started with. However, we can organize it by grouping similar terms together. We collect all the pieces that multiply the derivative of u with respect to xi into one group. Then we collect all the pieces that multiply the derivative with respect to eta into a second group. This algebraic rearrangement is crucial because it isolates the coefficients of our new partial derivatives, setting the stage for us to eliminate one of them entirely in the final step. This brings us to the final result of our derivation. To achieve the simplified canonical form, our goal is to eliminate one of the derivatives entirely. We do this by forcing the large coefficient in front of the xi derivative to be exactly equal to 0. From the established theory of differential equations, this specific condition is mathematically equivalent to solving the ordinary differential equation we saw earlier, the characteristic equation. By choosing xi to be the constant of integration from this equation, the entire first term vanishes. We can then define a new coefficient, capital E, to represent the remaining group. The equation now only has one derivative, reducing it successfully to its canonical form. The intuition here is that we deliberately built a coordinate system that perfectly absorbs the complexity of the original equation. Before we conclude, let us look at why canonical forms matter in the real world. Engineers and physicists hate unnecessary complexity when solving real-world problems. When modeling fluid flowing through a pipe, heat transferring across a metal engine block, or traffic flowing down a highway, the raw mathematical equations are often too tangled to solve directly. By converting these models into canonical forms, scientists can find exact analytical solutions instead of relying on heavy, error-prone computer simulations. It allows us to see the characteristics, which are the actual physical paths that information travels along, like the exact path a sound wave takes through the air. Without canonical forms, we would be stuck guessing solutions to messy equations, making it impossible to design safe airplane wings or predict weather patterns accurately. Let us summarize the key takeaways from this topic. First, the canonical form of a first-order partial differential equation is its simplest possible version, achieved by changing the coordinate system. Second, we use the characteristic equation to find new variables that eliminate one of the partial derivatives entirely. Third, this mathematical transformation turns a difficult multivariable problem into a straightforward single-variable problem. You have now seen how to apply this to both constant and variable coefficients and proven why the transformation works. Ultimately, this is a powerful mathematical tool for untangling complex physical systems and finding exact solutions. You have covered the full topic beautifully, and you are now ready to tackle these equations with confidence.